Let's talk about how to build production grade chat systems at scale. Building a chat system that handles 100 million concurrent users with, let's say, sub 500 millisecond latency while keeping infrastructure costs sustainable is an entirely different engineering challenge. This is a gap that we need to understand. The architectural requirements diverge significantly as we scale. A prototype handles thousands of connections on one server. However, a production system must orchestrate millions of persistent WebSocket connections distributed across a global infrastructure. We need strict message ordering guarantees even when messages route through the different servers. We need to handle viral group chats that can generate enough traffic to overwhelm individual database shards. And we need to do all of this within a budget that makes business sense. Consider some operational realities that don't appear in tutorials. When we restart a single gateway server for deployment, thousands of connected users disconnect simultaneously. Then they all try to reconnect at the same time, creating a thundering herd that can cascade into a broader outage if we have not designed for it. A popular group chat can generate traffic patterns that saturate individual cache nodes. If a celebrity posts in a 10,000 member group and members are actively responding, the right amplification and delivery fan out can strain the entire system. Message storage grows continuously as well. At billions of messages per day, we are adding terabytes daily. Without intelligent tiering strategies, storage costs alone become pretty unsustainable. Push notifications to millions of offline users can actually cost more than our compute infrastructure if we are not careful about throttling and batching. The takeaway here is that production chat systems require deliberate architectural decisions at every layer. We are not just scaling up a prototype, we are solving for fundamentally different problems. Now let's define exactly what our system needs to do. Let's talk about functional requirements for our chat system. One-on-one messaging forms the foundation. Users send text messages to other users in real time. The key constraint here is latency. Message delivery from sender to recipient should complete in under 500 milliseconds for users on reasonable network connections. Users have been trained by existing chat applications to expect near instantaneous delivery. Anything slower than that feels pretty broken. The system should also support message history. Users expect to scroll back through their previous conversations, potentially months or even years of messages. This means we need efficient storage and retrieval for historical data, not just real time delivery. Group chat extends messaging to multiple participants. Users create groups, they add members, and then send messages visible to all participants. Our design should handle groups of up to, let's say, 500 members efficiently. This threshold covers the vast majority of real world use cases while keeping fan out complexity pretty manageable. Now, groups larger than 500 members do exist. Broadcast channels with thousands or tens of thousands of followers require different architectural patterns, which we'll discuss when we cover fan out strategies. But for core group chat functionality, 500 members is a reasonable target. Online presence indicates whether a user is currently active. This seems simple but creates a significant challenge at scale. When a user comes online, we potentially need to notify hundreds of their contacts. When millions of users come online during morning hours, the notification volume explodes. We'll cover presence and optimization strategies in detail as well. Read receipts show message delivery and read status. The sender should know when their message reached the recipient's device and when the recipient should actually view the message. This requires tracking state per message per recipient, which adds storage overhead and creates its own fan out challenges for group messages. Push notifications alerts users when the application is not active. When users are offline or the app is backgrounded, we reach them through the platform services like APNs for iOS and FCM for Android. Notification costs can become significant at scale, so we need deliberate throttling and batching strategies. The takeaway is that each of these features has hidden complexity that emerges at scale. Our architecture needs to account for all of them. Now let's define the non-functional requirements that constrain our design. Latency is paramount for real-time communication. Message delivery from sender to recipient should complete in under 500 milliseconds under normal conditions. Users perceive delays beyond the threshold, and this experience gets really degraded pretty noticeably. This latency budget must account for everything: message processing, storage writes, routing lookups, and delivery across potentially intercontinental infrastructure. Every component in this path consumes part of this budget. Availability should target at least 99.99% uptime. Chat is the primary communication channel for many users. They expect it to work whenever they need it. This uptime target translates to roughly 52 minutes of downtime per year. Achieving this requires redundancy at every architecture layer, graceful degradation where individual components fail, and the ability to perform maintenance without service disruption. Message ordering must be preserved within a conversation. If a user A sends hello followed by how are you, these messages must appear in that order for all participants. This sounds pretty obvious, but achieving strict ordering while maintaining low latency across distributed architecture is generally pretty hard. Messages may route through different servers with slightly different clocks. Network delays can cause the messages to arrive out of order, and our pipeline design must handle all of these cases. Durability means no message loss should happen under any circumstance. Once we acknowledge a message to the sender, it must eventually reach the recipient. Even if servers crash, networks partition, or users stay offline for extended periods, that should still happen. This invariant requires synchronous writes to durable storage before we send acknowledgement. We cannot acknowledge and then persist asynchronously, or we risk losing messages. Horizontal scaling should support growth from thousands to millions of concurrent users. The architecture should scale by adding more machines rather than requiring larger individual servers. This applies to connection handling, message processing, and storage. No single component should become a bottleneck that limits overall system growth. The key insight is that these requirements often tension against each other. Low latency wants to skip the database write. Durability demands that we complete it. Our architecture must balance these competing concerns. Now let's put concrete numbers to these requirements. Now let's talk about capacity estimation with concrete numbers. We'll use 100 million daily active users as our reference scale. This represents a large chat application comparable to major messaging platforms. Each user sends approximately 40 messages per day on average. This gives us 4 billion messages daily, which translates to roughly 50,000 messages per second at a steady state. But a steady state is not what breaks systems. Peak traffic is what breaks systems. We should estimate peak traffic at least 3 to 5 times the average throughput. This means designing for 200k messages per second during high activity periods like evenings and holidays. So that's 200,000, which is roughly the 4 times of 50,000 that we calculated earlier. Now, concrete connections at peak might reach 10% of our daily active users. That's 10 million simultaneous WebSocket connections. Each WebSocket connection consumes server memory for socket buffers and session state. Depending on implementation, this ranges from 10 to 50 kilobytes per connection. At 10 million connections with 20 kilobyte average, we need 200 GB of memory just for connection state. Not for messages, not for processing, just for the connection state. So just for holding the connections open. Storage grows pretty significantly as well. Each message averages around 100 bytes of text content plus 200 bytes of metadata, including the timestamps, IDs, sender information, and index entries. At 300 bytes per message and 4 billion daily messages, we add roughly 1.2 terabyte of new message data per day. With a replication factor of 3 for durability, this becomes 3.6 terabyte daily. Over a year, we're looking at over 1 petabyte of message storage. Bandwidth calculations must account for message fan out. A message to a 100-member group generate 100 outbound deliveries. If 10% of message volume targets groups averaging 20 members, the effective delivery rate multiplies by roughly 3x compared to the raw message rate. The takeaway is that capacity planning requires working through these numbers explicitly. Assumptions that seem reasonable can be widely off at a scale. Now let's translate those capacity requirements into the cost. Now let's talk about economics of running a chat system at scale. Compute costs for connection handling dominate in chat systems, which differs from typical web applications where compute scales with request rate. In chat systems, we're holding millions of persistent connections, and each connection consumes memory whether or not messages are flowing. At 10 million concurrent connections requiring 200 GB of aggregate memory and using instance with 64 GB RAM each, we need at least 4 to 5 gateway servers just for memory. Factor in the CPU for message routing, TLS termination, and heartbeat processing, and the count keeps increasing. At a typical cloud pricing, gateway infrastructure for 10 million connections runs tens of thousands of dollars per month. Storage costs scale with message volume and retention period. Storing 1 terabyte of messages annually using replicated SSD storage gets expensive pretty quickly. The solution is tiered storage. Keep the last 30 days of messages on fast SSD backed storage for active retrieval. Move older messages to cheaper archive storage, potentially HDD backed or cloud core storage tiers. This approach can reduce storage costs by 70% or more while maintaining access to full message history when users need it. Bandwidth costs accumulate from message delivery, especially for media. Text messages are small, but image and video delivery can dominate bandwidth bills. CDN distribution and intelligent caching help reduce egress costs. Compressing message payloads before transmission helps for text-heavy workloads. Push notifications costs are often overlooked in initial estimates. APNs for iOS is free, but high notification volume can trigger rate limiting or require enterprise agreements with providers. More importantly, if we are sending 50 notifications when a user has 50 unread messages, we are wasting money and annoying users. Notification throttling and batching strategies are essential for both cost control and user experience. The key practice is to model costs and tech 10x and 100x current scale before committing to an architecture. Some costs scale linearly while others have step functions when crossing infrastructure thresholds. Now let's design the high-level architecture to meet these requirements within these constraints. Now let's talk about high-level architecture and how the component fits together. Clients connect through mobile applications, web browsers, or desktop applications. Each client maintains a persistent WebSocket connection for real-time bidirectional communication. Native mobile applications have advantages here. They support the background processing for notifications and efficient battery management. Web clients face browser lifecycle limitations that affect the connection persistence. Load balancers distribute the incoming connections across gateway servers. For WebSocket traffic, load balancers must maintain connection affinity because WebSocket is stateful. Unlike HTTP, where each request can go to any server, WebSocket messages must route to the specific server holding that connection. Layer 4 load balancing works well here, making routing decisions at connection time based on TCP characteristics rather than inspecting the HTTP content. Gateway servers handle connection management. They maintain WebSocket connections with clients, handle authentication, process heartbeats, and route messages to backend services. Gateways are optimized for high connection counts and minimal per message processing. They delegate all business logic to other services, staying focused on their core job of connection management. Chat servers contain the core messaging logic. They process the incoming messages, validate the permissions, coordinate with storage, determine the delivery targets, and route messages to recipients. Chat servers are stateless with respect to connections. They do not know or care which gateway holds which user. This separation allows chat servers to scale independently based on message volume rather than connection count. Data stores include the message database, session store, cache layer, and media storage. Each is optimized for its specific access patterns. The message database handles durable persistence with conversation-based access patterns. Redis manages sessions and caching. Object storage handles the media files with CDN distribution. The key architecture principle is separation of concerns. Each component has a focused responsibility and scales according to its own constraints. Now let's trace the complete path of a message through this architecture. Now let's talk about how a message flows from sender to recipient through our architecture. Understanding this end-to-end flow is essential for identifying bottlenecks and failure points. Each step consumes part of our latency budget and represents a potential failure node. The flow begins when the sender's client transmits a message over its WebSocket connection. The message includes recipient information, content, client timestamp, and a client-generated ID for deduplication. The client immediately displays the message locally with the pending status, providing instant feedback while the actual delivery proceeds. The gateway server receives the WebSocket frame. It extracts the user identity from the authentication session and forwards the message to an available chat server. The gateway performs no business logic here, only routing. This keeps gateways simple and fast. The chat server validates the message, it verifies the sender has permission to message the recipient, applies rate limiting to prevent abuse, checks the content format, and generates server-side message ID and timestamp. After validation passes, it writes to the database synchronously. The synchronous database write is pretty important. The message must be on disk before we acknowledge to the transfer to the sender. This ensures durability. If we acknowledge first and then crash before the persisting, the message would be lost. Users trust that a send checkmark means that their message is safe. Once the storage confirms the write, the chat server acknowledges receipt to the sender. This acknowledgement flows back through the gateway to the client. The client then updates this message status from pending to sent. The chat server then initiates a delivery by looking up recipient connection locations in the session store. For each online recipient, it pushes a message to the appropriate gateway. For offline recipients, it queues a push notification. This delivery happens asynchronously from the acknowledgement, so the sender sees confirmation quickly even if delivery takes longer. Now let's examine how we divide responsibilities between different components. Now let's talk about component ownership boundaries and why they are important. Clear boundaries enable independent scaling, deployment, and team ownership. Each component has specific responsibilities and well-defined interfaces with other components. When boundaries are fuzzy, changes become pretty risky because they might affect multiple systems in unexpected ways. Gateway servers own connection lifecycle. They handle the WebSocket establishment, authentication, heartbeat monitoring, and graceful disconnection. Gateways know nothing about message content or routing logic. Their metrics focus on connection counts, memory usage, and message throughput. A team operating gateways cares about connection capacity and network efficiency, not message semantics. Chat servers own the messaging business logic. They handle the message validation, ordering, storage coordination, and routing decisions. They interact with gateways through internal protocols but do not manage client connections directly. Their metrics focus on message processing latency and error rates. The team here cares about the correctness and processing efficiency. Storage services own the database persistence and retrieval. This includes the message database, conversation indexes, and caching layers. Storage interfaces are designed for specific access patterns of chat workloads, which are primarily write and conversation based reads. The storage team cares about durability, query performance, and capacity planning. Notification services own the offline delivery. When recipients lack active connections, this service manages push notification formatting, provider communication, and delivery tracking. It operates asynchronously from the main message path. This isolation means notification provider issues do not affect the real-time message delivery. Media services own the file storage and processing. Upload handling, thumbnail generation, virus scanning, and CDN distribution is handled here. Media is referenced by the ID in messages but stored separately with its own scaling characteristics. The key insight is that good boundaries let each component evolve independently. We can rewrite the notification service without touching the message processing logic. Now let's dive into the transport layer, which is starting with the protocol selection. Now let's talk about transport protocol selection and why WebSocket is the standard choice for chat systems. HTTP polling has clients repeatedly requesting new messages at fixed intervals. With a 1 second polling interval and 10 million users, we generate 10 million requests per second even when no messages exist. The vast majority of these requests return empty responses. This wastes server resources, wastes clients' battery life, and introduces latency up to the polling interval. If we poll every second, messages can take up to a second to appear. This is not suitable for real-time production chat systems. Long polling improves efficiency by having the server hold request open until data arrives or a timeout occurs. This eliminates most of the empty responses. However, long polling still requires reconnection after each message or timeout. Each reconnection involves TCP handshake, TLS negotiation, and HTTP headers. This overhead adds latency and limits the throughput. Server send events provide server to client streaming over HTTP. The server pushes data as it becomes available. This works well for one-way real-time updates like notifications or feeds. However, chat requires bidirectional communication. Users send messages too, so with SSC, which is server-side events, we would need a separate channel for sending, complicating the architecture as a whole. WebSocket establishes a persistent bidirectional connection. After an initial HTTP handshake that upgrades the protocol, both client and server can send messages at any time with minimal framing overhead. A WebSocket frame is just a few bytes of header plus the payload. This is a standard choice for production chat systems. The trade off here is operational complexity. WebSocket connections are stateful and long lived. Server restarts affect the connected users. Load balancing requires connection awareness rather than simple round robin. Connection state consumes memory for the lifetime of the connection, and these challenges are manageable and worthwhile for true real time bidirectional communication. And this is just something as part of production system we have to build. Now let's examine the specific challenges that emerge when running WebSocket at scale. Let's talk about challenges that emerge when running WebSocket at production scale. Memory pressure accumulates with connection count. Each connection requires socket buffers, session state, and application level data structures. At 100,000 connections per server with 20 kilobyte per connection, a single gateway needs 2 gigabytes just for connection state. This does not include the memory for processing messages or other application needs. Memory becomes the primary scaling constraint for gateway servers, not CPU. File descriptor limits constrain the connection counts at the operating system level. Each WebSocket connection is a file descriptor. Linux defaults often allow only 1024 file descriptors per process, which is widely insufficient for a production gateway. We must configure higher limits at both process level using ulimit and system level and kernel parameters. Monitor file descriptor usage and alert as we approach the configured limits. Load balancing stateful connections differs fundamentally from stateless HTTP. We cannot route each message to any available server. The connection lives on a specific gateway, and all messages for that connection must reach that gateway. Load balancers must support connection affinity and handle WebSocket upgrade handshakes correctly. Some load balancers struggle with the protocol upgrade from HTTP to WebSocket. Health checks for WebSocket servers should verify WebSocket functionality, not just the HTTP response. A server might respond to HTTP health checks while being completely unable to accept new WebSocket connections due to memory exhaustion or file descriptor limits. You should include connection count and resource metrics in health check responses as well. Deployment requires connection draining. We cannot simply terminate a server with 100,000 connections. That would disconnect 100,000 users instantly. Graceful shutdown stops accepting new connections while existing connections remain active. Users naturally reconnect to other servers over time due to network events, app start restarts, and deep device sleep cycles. This allows sufficient drain time before terminating the old server. Now let's design the gateway servers that manages these connections. Let's talk about designing gateway servers that handle massive connection counts efficiently. Connection acceptance should be optimized for throughput. Use asynchronous I/O models like ePOL on Linux or KQ on BSD systems. These allow a single thread to efficiently monitor thousands of sockets for activity. Single thread event loops can handle tens of thousands of connections efficiently because most connections are idle most of the time. They accept the queue should be the size to handle connection bursts without dropping incoming connections during traffic spikes. Authentication happens immediately after WebSocket establishment. The client sends credentials or an access token in the first message after the connection opens. The gateway validates against the auth service before allowing any other operations. Invalid or expired credentials trigger the immediate connection termination. We don't want to waste resources on unauthenticated connections. Session registration records which gateway holds each user's connections, so the information goes to a distributed store like Redis. The session record includes the user ID, gateway server identifier, connection timestamp, device information, and client version. Other services query the store to route messages to the correct gateway. Without accurate session state, we cannot deliver messages. Topic subscription configures which message this connection should receive. Topics include direct messages to this user, group memberships for group messages, and present subscriptions for online status contacts. The pub/sub pattern enables the efficient fan out. When a message arrives for a group, we publish to a group topic and all the subscribed connections, then they receive it. The message loop is a steady state operation after setup completes. The gateway reads incoming frames from the client and forwards them to chat servers. It receives the messages from internal services and writes them to a client WebSocket. This loop continues until the connection closes due to client disconnect, network failure, or server shutdown. Now let's examine how to load balance these stateful connections. Let's talk about load balancing WebSocket connections, which require different approaches than stateless HTTP. Layer 4 load balancing operates at a TCP level. It routes connections based on IP addresses and ports without inspecting the HTTP content. This works well for WebSocket because the load balancer makes a routing decision once at a connection establishment time and then forwards all subsequent traffic bidirectionally without further intervention. The load balancer does not need to understand WebSocket frames or maintain application state. Connection affinity ensures all traffic for an established connection reaches the same backend server. Without affinity, WebSocket frames could route to servers that do not hold the connection, causing the failures. Most layer 4 load balancers maintain affinity automatically per TCP connection because they are simply forwarding packets for an established connection. Server selection algorithms should consider current connection counts, not just the request rates. Round robin ignores the service load entirely, so a server that just got restarted gets the same traffic share as one which is almost at capacity. Least connections routing directs the new connections to server with fewer existing connections, achieving better balance. So we should also weight servers by memory capacity since connections consume memory. Handling server removal requires draining. When taking a server out of rotation for deployment or maintenance, we stop sending new connections but maintain existing ones. Connections drain naturally as clients reconnect due to app restarts, network changes, and deep device sleeping cycles. Allow sufficient drain times, typically around 15 to 30 minutes before forcefully terminating remaining connections. Health checking should verify connection capacity, not just server liveness. A server and memory limit should be marked unhealthy for newer connections even if existing connections function correctly. Include the connection count and memory usage in health responses. The load balancers should stop routing new connections to saturated servers. Now let's address one of the most dangerous failure modes in connection-heavy systems. Let's talk about thundering herd problem, which can turn a minor issue into a major outage. Consider a gateway server holding 100,000 connections that restarts for deployment. All 100,000 clients detect disconnection within seconds. By default, clients immediately attempt reconnection. The remaining gateway servers suddenly receive a flood of 100,000 connection requests in a very short window. Each new connection involves TCP handshake, TLS negotiation, WebSocket upgrade, authentication against the auth service, and session registration in Redis. The CPU cost multiplies across all these operations. The auth service receives a spike of validation requests. Redis receives a spike of session writes. Any components running at or near capacity under normal load now will be overwhelmed. When components fail under load, connection attempts fail. Clients retry. Failed retries generate even more load, and the system enters a death spiral where the retry traffic prevents the recovery. What started as a single server restart cascades into a broader outage. Mitigation for this requires client-side backoff. Clients should not retry immediately and upon disconnection. You should be implementing exponential backoff with jitter. The first retry happens after a random delay of between, let's say, 1 to 5 seconds. If that fails as well, then we wait 2 to 6 seconds, then 4 to 12 seconds. Double the range each time up to a maximum of perhaps 60 seconds. And jitter is pretty critical. Without randomization, clients that disconnected together will retry together even with exponential delays. The 100,000 clients all wait 2 seconds, then all retry exactly the same moment. Jitter spreads the retries across the window, converting a spike into a manageable ramp. Server-side protection includes connection rate limiting, both per IP and globally. Admission control can temporarily reject new connections when the system is overloaded, returning a retry later response that instructs clients to back off. Gradually ramping up a new server before exposing it to full traffic also helps. Now let's examine how we track which users are connected to which gateways. Now let's talk about session state management, which is fundamental to message routing. When a message arrives for user A, the system must know which gateway server holds user A's connection. Without this mapping, we cannot deliver messages. Session state provides this mapping. Redis is a common choice for session storage. It provides sub-millisecond lookups, which we need because we query session state for every message delivery. It supports automatic expiration through TTL, which handles cleanup when connections die unexpectedly, and it offers PubSub capabilities for presence notifications. Session data includes user ID, gateway server identifier, connection timestamp, device type, client version, and subscription list. You should be writing the session record immediately after authentication succeeds. Include a TTL slightly longer than the heartbeat interval, typically between 60 to 90 seconds. If the connection dies without proper cleanup, the session expires automatically rather than leaving stale entries that cause delivery failures. A reading session state happens during message routing. The chat server looks up recipient sessions to determine delivery targets. For one-on-one messages, this is a single lookup. For group messages, this involves looking up sessions for all group members, which can be expensive for large groups. Consider caching member list and session state for active conversation. Deleting session state should happen on clean disconnection. You should not be relying solely on TTL expiration. When a client disconnects cleanly, remove the session asynchronously. This will ensure that subsequent messages correctly identify the user as offline and trigger push notifications instead of attempting WebSocket delivery that will fail. Multi-device scenarios complicate session management. One user may have multiple active connections from phone, tablet, and computer. The session store should accommodate multiple entries per user, each representing a different device. Messages should deliver to all active devices, not just one. Now let's examine what happens when a gateway server fails unexpectedly. Now let's talk about handling gateway server failures, which are inevitable in any distributed system. When a gateway crashes, all its connections terminate immediately. Clients detect this through WebSocket close events, even if shutdown was graceful, or through failed heartbeats if it wasn't. The session entries in Redis remain temporarily until the TTL expires, which is typically 60 to 90 seconds. This TTL creates a window for stale routing. Messages sent to users whose sessions still point to the dead gateway will fail delivery. The chat server attempts to push to the dead gateway, the push fails, and we need a fallback path. The chat server should handle delivery failure pretty gracefully. So if pushing to a gateway fails, you should not be just stopping and dropping the message. You should be checking if it's a transit failure worth retrying. If the gateway is truly gone, fall back to the offline message queue. The message will be delivered when the user reconnects. For urgent messages, trigger a push notification as well. Client reconnection follows the backoff strategy we discussed earlier. Jittered exponential backoff prevents the thundering herd problem on the remaining gateways. The load balancer assigns the reconnecting clients to healthy servers using its normal selection algorithm. New session registration occurs after reconnection and authentication. The old session either expired naturally or gets overridden by the new session. The user is now reachable at their new gateway location. Any messages that accumulated in the offline queue during the failover window will get delivered. Message recovery ensures nothing is lost during the failover window. The offline message queue is the safety net. Messages that could not be delivered in the real time wait there until the user reconnects. This is why we persist messages before acknowledging the senders. The durability guarantee holds even those server failures. Now let's look at the client side of reconnection handling. Let's talk about implementing reconnection logic on the client side, which significantly impacts system stability. Poorly implemented connection can cause or amplify outages. A client that retries aggressively turns every blip into a 13-herd problem. Good reconnection logic protects both the client and the system. You should be detecting disconnection through multiple signals. WebSocket close events indicate a clean server-initiated disconnection. The server decided to close the connection, perhaps for maintenance. Failed heartbeat responses indicates the network issues or server failure. The server did not explicitly close but is not responding. Both the conditions should trigger reconnection logic, but we might handle them slightly differently. Initial delay prevents the immediate retry. You should be waiting a random period between 1 and 3 seconds before the first reconnection attempt. This randomness provides significant protection when many clients disconnect simultaneously. Even with full exponential backoff, just this initial jitter helps pretty much. Exponential backoff increases the delay between subsequent events. If the first retry fails, you should be waiting 2 to 6 seconds, then 4 to 12 seconds, then 8 to 24 seconds. You should be doubling the range each time up to a maximum, typically 60 seconds. This prevents the clients from hammering a struggling system which might also already be down. And jitter randomizes within each Backoff window. If our calculated delay is 8 seconds, pick a random value between 8 and 16. Without jitter, clients that connect together will synchronize their retries at exactly 1, 2, 4, 8 seconds, maintaining the spike pattern. Maximize the retry duration limits how long clients attempt the reconnection. After several minutes of continuous failures, something is seriously wrong. You should be showing an error state in the UI and stop automatic retries. You should require the user interaction to try again. This prevents the battery drain from endless background reconnection attempts on mobile devices. Connection state UI should keep users informed. You should show clear indicators for connected, and disconnected states. Users should also know when their message might not be sent immediately. Now let's move to the message processing layer and examine chat server design. Now let's talk about designing chat servers that processes the message efficiently. Chat servers contain the core messaging business logic. Unlike gateways which are optimized for connection count, chat servers are optimized for message throughput and processing correctness. They are stateless with respect to connections, which means any chat server can process any message. Chat servers receive messages from gateway servers through internal RPC or message queues. The gateway forwards the raw client message along with the authenticated user context. Because chat servers do not maintain the client connections, they can scale independently based on message volume. If we need more message processing capacity, we add chat servers without touching the gateways. Validation is the first processing step. Does the sender have permission to message the recipient? Are they friends? Are they both members of the same group? Is the message format valid? Does the content violate any policies? Is the sender within rate limits? You should be rejecting invalid messages with appropriate error codes that the client can display to the user. ID generation assigns server-side identifiers. Clients provide their own IDs for deduplication, but server IDs ensure global uniqueness and correct ordering. We generate time-sortable IDs like ULID or Snowflake format. The server then also assigns the authoritative timestamp. Client timestamps are unreliable due to the clock skew. Persistent writes the message to the durable storage continuously. So this is a critical step. The message must be on disk before we acknowledge to the sender. If we crash after acknowledgement but before persistence, the message is lost and the user was lied to about it being sent. Routing determines delivery targets after persistence. So look up the recipient sessions. For online users, push to their gateway servers. For offline users, trigger the push notification. For group messages, fan out to all members. Routing happens asynchronously after the write confirms, so the acknowledgement latency is not affected by SO deliveries. Now let's trace the send path in detail. Let's talk about the send path, which is the latency sensitive critical path for message sending. Users expect send messages to appear confirmed quickly. Every millisecond in this path affects the perceived responsiveness. The send path ends when the server sees the send checkmark, not when the recipient receives the message. The client prepares the message with content, recipient, and a client-generated request ID. This request ID enables the independency. If the client times out max waiting for the acknowledgement and retries, the server can detect the duplicate using this ID and return the same response without reprocessing or creating the duplicate messages. The gateway receives the WebSocket frame, identifies an authenticated user from the session state, and forwards to a chat server. Gateway selection can use round robin or least load routing among available chat servers. The gateway itself performs manual processing here. The job is to move the bytes efficiently. The chat server validates and processes the message. This is the most CPU intensive steps in the send path. Validation, ID generation, and any content processing like link transaction, extraction, or mention detection happens here. You should be keeping this fast by deferring non-essential work to asynchronous pipelines. The database write must complete before acknowledgement. Use the faster write path available. Write to the primary replica with synchronous replication to at least one secondary to ensure durability. Asynchronous replication to additional replicas can happen after acknowledgement. Acknowledgement returns to the sender through the gateway. Include the chat server assigns message ID and timestamp. The client updates its local message state from pending to sent and stores the server ID for future reference. Total send path latency should target under 100 milliseconds for the common case. Now let's examine the receive path that delivers a message to the recipients. Now let's talk about the receive path, which delivers the messages to recipients after persistent. The receive path can happen asynchronously from the send acknowledgement. The sender sees send status before recipients necessarily receive the message. This decoupling keeps the send path fast by allowing delivery to take whatever time it needs. Recipient lookup depends on message type. For one-on-one messages, there is a single recipient. For group messages, we fetch the current member list. The member list should be cached because they change infrequently compared to the message volume. A group that exchanges thousands of messages might only change membership a few times per month. Session lookup finds which gateways hold recipient connections. Query Redis for each recipient session. Recipients without active connections are offline and need push notification instead of the WebSocket delivery. This lookup is on the critical path for delivery latency, so Redis performance matters. Gateway push sends a message to each relevant gateway server. Use efficient internal protocols, not full HTTP for each push. Batch messages destined for the same gateway when possible. Include the recipient user ID so the gateway knows which of its thousands of connections should receive the message. Client delivery completes when the gateway writes to the recipient's WebSocket. The recipient's client receives the message and displays it in the conversation. The client should send a delivery acknowledgement back, which propagates through the system to update message status for the sender. Parallel delivery is essential for group messages. Sending to 100 recipients sequentially would take far too long. Fan out to multiple gateways in parallel. The chat server should not be blocking, waiting for all deliveries to complete before processing the next message. Fire off the deliveries and then move on. Now let's examine how we generate message IDs that support our ordering and query requirements. Let's talk about message ID generation, which directly impacts our query efficiency and system scalability. We need IDs that satisfy several requirements simultaneously. They must be globally unique across the entire system. With billions of messages, collision probability must be negligible. They must be generated without coordination. Multiple chat servers create IDs simultaneously, and we cannot have them consulting a central service for every message. And they should also be time sortable so that the queries by ID return messages in a chronological order. Snowflake format, originally developed at Twitter, packs timestamp, machine ID, and sequence number into 64 bits. The first 41 bits encode millisecond timestamp, giving us about 69 years of range. The next 10 bits identify the generating machine, following the 1024 unique generators. The final 12 bits are a sequence number, allowing 4096 IDs per millisecond per machine. The math works out favorably. With 1024 machines, each generating 4096 IDs per millisecond, we can create over 4 million IDs per millisecond globally. That's well beyond our peak message rate requirements. And because the timestamp is a higher order bits, IDs sort chronologically. ULID provides similar properties in 128 bits with a different encoding, 48 bits of timestamp followed by 80 bits of randomness. ULIDs sort lexicologically by time when encoded as strings, which is convenient for databases that handle strings more naturally than 64-bit integers. Clock synchronization matters for distributed ID generation. If one server's clock is ahead by a second, its messages will sort after messages from other servers even if they actually happened earlier. You should be using NTP to synchronize clocks and monitor drift. A small drift of a few milliseconds is acceptable. Large drift corrupts the ordering and needs immediate attention. Now let's examine how we guarantee message ordering within conversations. Let's talk about message ordering, which users expect to just work but requires careful implementation. Client timestamps are fundamentally unreliable. Device clocks can be wrong, deliberately manipulated, or drifting without the user's knowledge. Never use client timestamps for authoritative ordering. We can accept them as a metadata and display them to the user, but ordering decisions must use server assigned values. Server timestamps from a single server provide consistent ordering. When all messages from a conversation route through the same server, that server can assign strictly increasing timestamps or sequence numbers. Ordering is straightforward because one authority controls the sequence. The challenge emerges with multiple chat servers. Different servers have slightly different clocks even with NTP synchronization. If users A message routes through server 1 and users B message routes through server 2, Clock skew can actually cause ordering anomalies. Users B's message might get a lower timestamp despite being sent slightly later. Single writer per conversation eliminates the cross-server ordering issues. You should be routing all messages for a given conversation to the same chat server using consistent hashing on the conversation ID. This server becomes the sequencing authority for that conversation and assigns the increasing sequence numbers. Trade-offs do exist with single writer approach. It limits horizontal scaling per conversation. A very active conversation bottlenecks on one server. For most conversations, this is perfectly fine. Activity levels that would strain a single server are pretty rare. For viral group chats that might actually hit this limit, we can accept slightly weaker ordering or implement more sophisticated sequencing with distributed coordination. Display order on clients uses the sequence numbers of server timestamps. Clients sort messages by this value. Late arriving messages insert into the correct position rather than appending at the end. The UI should handle these insertions smoothly without jarring the visual jumps. Let's examine the delivery semantics and what guarantees we can provide. Let's talk about delivery semantics, which define what guarantees our system provides. At most, one delivery means messages may be lost but will never be duplicated. This is simplest to implement. Send the message and forget about it. If something fails, don't retry. For chat messages, this is unacceptable because users cannot tolerate lost messages. At least once delivery means messages will eventually be delivered but may be duplicated. We achieve this through persistence and retry. Write the message to the durable storage, attempt the delivery. If the delivery acknowledgement isn't retrieved, retry. The message might have been delivered and only the acknowledgement lost, but we cannot tell, so we retry anyway. This may create duplicates, by the way. Exactly once delivery means messages are delivered once and only once. This is the ideal experience, so this means no lost messages and no duplicates. However, it's more expensive to implement because it requires coordination to detect and suppress duplicates while still guaranteeing delivery. The practical approach for chat systems is at least once delivery with client-side duplication. The server guarantees the message will arrive possibly multiple times. The client uses the message ID to detect duplicates. When receiving a message, the client checks if this ID already exists in the local storage. If so, it ignores the duplicate. This check is cheap and effective. Server side exactly once would require tracking delivered message IDs per recipient persistently. We would need to store and query the state for every delivery. This overhead usually is not justified when clients can deduplicate so easily. The key insight is that we can achieve the user experience of exactly once in delivery without the implementation complexity by pushing deduplication to clients. Now let's examine how duplicates arise and how we handle them. Now let's talk about why duplicates occur and how we handle them systematically. Duplicates are inevitable in any distributed system with delivery guarantees. Accepting this reality and designing for it is more effective than trying to prevent duplicates entirely. Server-side duplicates happen when the clients retry a send due to the timeout. The user hits send, the message is processed and persisted, but the acknowledgement is lost in the network. The client times out and retries. The server receives what message appears to be a new message. Without deduplication, we would store it twice. The solution is client request IDs. Each send attempt includes a unique request ID generated by the client. Before processing, the server checks if we have seen the request ID recently. If so, we return the same response without reprocessing. This makes retries safe. Delivery side duplicates happen when the delivery acknowledgement is lost. The server sends the message to the receiver in gateway. The gateway delivers it to the client. The client stores the message and sends a delivery acknowledgement. The acknowledgement is lost. The server does not know delivery succeeded, so it might retry. The recipient sees the message twice. Client-side deduplication handles this. When receiving a message, you should be checking if the message ID already exists locally. If so, you should ignore the duplicate. This check is a simple local database lookup, adding the negligible overhead. At idempotency window limit how long we remember the process request. We cannot track every request ID forever. You should be using a time window based on a retry policy. If retries happen within 5 minutes, keep request ID for 10 minutes. After that, we assume any duplicate would have been caught. Now let's examine the acknowledgement protocol that tracks the message state. Let's talk about acknowledgements, which track message state through its complete lifecycle. A well-designed acknowledgement protocol provides visibility into delivery status without generating excessive traffic. Users want to know their message was sent and delivered and read. We need to provide this information efficiently. You should be sending acknowledgement confirms that the server has received and processing the message. There is a commitment that the message won't be lost. When the client receives the acknowledgement, it can safely display the message as sent. This acknowledgement must be fast because users are waiting. It should complete within the 100 milliseconds of the user hitting send. Delivery acknowledgement confirms the message has reached the recipient's device. The receiving client sends this acknowledgement after successfully storing the message locally. The acknowledgement propagates back through the system to update message status. The sender can now display it as delivered. This involves a round trip through the server, so it takes longer than the send back the acknowledgement. A read acknowledgement confirms that the recipient actually viewed the message. This triggers when the conversation containing the message becomes visible in the recipient's application. The message might have been delivered hours ago but only read now. The sender can display the read status with a timestamp. Batching read acknowledgement is essential for efficiency. Opening a conversation with 100 unread messages should not generate 100 individual acknowledgements. Send a single acknowledgement with the ID of the most recent message read. The server will mark all messages up to that ID as read for the recipient. Acknowledgement delivery should be reliable but can also be asynchronous. If a delivery acknowledgement is lost, the consequence is only cosmetic. The sender does not see the delivery status update, but the message was delivered. This does not need the same reliability guarantees as the message delivery itself. Now let's move to the storage layer, starting with the database selection. Let's talk about database selection for message storage when it involves real trade-offs rather than a single and right answer. Write throughput is the primary constraint for message databases. Billions of messages daily means actually tens of thousands of writes per second continuously. This is not burst traffic that caching can absorb. It's sustained write load that the database must handle directly. Write optimization often matters more than the read optimization for chat workloads. Access patterns are primarily conversation based. Users fetch recent messages for conversation, then load messages as they scroll. The dominant query pattern is messages in conversation X ordered by time, most recent first. Range queries by conversation ID and message ID are the standard access pattern. Point lookups for individual messages are less common. Horizontal scaling is essential at production volume. No single database instance can handle billions of messages. The database must shard across many nodes while maintaining the query patterns we need. Native sharding support simplifies the operations compared to implementing the application level sharding ourselves. Cassandra offers excellent write performance with native horizontal scaling. Its wide column model suits message storage well. We can use conversation ID as a partition key and message ID as a clustering key. The trade-offs are the operational complexity and eventual consistency semantics that do require careful handling. PostgreSQL or MySQL with application level sharding works for teams with deep relational database expertise. We gain transactional guarantees and familiar tooling with it. We accept the responsibility for implementing and operating the sharding layer. The key is that matching the choice to our team's expertise and the operational capabilities. A database we can operate well beats the theoretically better database that we'll struggle with. Now let's examine the schema design for message storage. Now let's talk about schema design, which directly impacts the query performance. Partition key should be a conversation ID. This ensures all messages for a conversation reside on the same partition, enabling efficient RAGE queries for message history. When a user loads a conversation, we hit exactly one partition. All common queries can be served from a single partition without cross-partition coordination. Clustering key should be the message ID within the partition. Since our message IDs are time sortable, this maintains messages in chronological order within the partition. Queries for, let's say, last 50 messages in conversation X become a simple reverse scans from the end of the partition. No sorting is required as a query time. Message payload includes the content, sender ID, timestamps, and message types, and any attachments. Denormalize the sender information like display name and avatar URL at the right time. This would avoid joins when rendering message lists. The trade-off is that the sender info may be stale in old messages. If the users update their profiles, this is usually acceptable. Secondary indexes should be used sparingly. An index on a sender ID across all conversations enable queries like, let's say, all messages from user X but they do add write overhead to every message. Each write must also update the index. Only add indexes for queries we actually need. TTL can automate the data lifecycle for time-limited retention. Messages older than a retention period automatically expire or move to the archived storage. Configure the TTL based on a retention policy. Not all systems need infinite memory history. Now let's examine the conversation data model that organizes the messages. Let's talk about modeling conversations, which are the organizational unit for messages. Conversation ID uniquely identifies each conversation. For one-on-one chats, we can derive the canonical ID for the two participant IDs, sort the IDs, and combine them. This ensures the same conversation regardless of who initiated it. For groups, we assign a random or sequential ID at a creation time. Participant list contains the user IDs for all members. For one-on-one chats, we exactly have two users. For groups, we have potentially hundreds. Store as an array or a set with John timestamps and roles. Index for queries in both directions, groups containing user X and users in group Y. Metadata includes the conversation name, avatar, description, creation timestamp, and settings. One-on-one chats derives the name and avatar from the other participant. Groups have explicit metadata that members or admins can update. The last message references that enables efficient conversation list rendering. Instead of querying messages to find the most recent for each conversation, we cache the response on the conversation record. Updated when the new messages arrive, the conversation list page needs only one query for conversation metadata, including the last message preview. Per user metadata includes the rate position, mute status, and notification preferences. Each participant may have different settings for the same conversation. You should be storing this separately, keyed by the user ID and conversation ID. A user might mute a busy group while others may want every notification. Now let's examine the sharding strategy for message data. Let's talk about sharding, which is how we distribute data across multiple database nodes. Shard by conversation ID to keep related data together. All messages for a conversation land on the same shard. History queries don't span the shards. This is a dominant access pattern and must be optimized. The goal is that most queries hit exactly one shard. Consistent hashing maps the conversation ID to shards. We hash the conversation ID and map the hash to a shard. When adding or removing shards, only a fraction of data moves rather than reshuffling everything. You should be using virtual nodes for better distribution. Instead of 1 point per shard on the hash ring, you should be using hundreds. This smooths out the imbalances. Shard counts should anticipate the future growth. Starting with too few shards means painful rebalancing later when we run out of capacity. Starting with too many will add overhead for shard management. For large systems expecting billions of messages, thousands more shards is reasonable. Each shard handles manageable subset of conversations. So rebalancing moves the data between the shards when the cluster changes. This consumes network bandwidth and disk I/O. It can impact the production traffic if not throttled carefully. Designed for minimal rebalancing, adding the capacity should be routine, not a crisis that requires weekends of careful migration. Cross-shard queries are expensive and should be rare. Queries like scratch search all messages from user X across all conversations must touch every shard. You should be supporting these for administrative purposes, but don't build user-facing features that rely on them for normal operation. Now let's examine what happens when a single conversation generates disproportionate load. Let's talk about the hot conversation problem, which is the chat equivalent of hotkeys in other distributed systems. The problem emerges directly from conversation-based sharding. All messages for a conversation go to one shard. Normally this is exactly what we want, but when a conversation has thousands of active users sending messages continuously, that shard receives disproportionate load. Consider a celebrity group chat with 10,000 members during a live event. Members are excited and they're sending messages rapidly. Every message writes to the same shard. Every message fans out to the 10,000 recipients. The shard handling this conversation receives orders of magnitude more traffic than average shards. Detection requires monitoring per conversation metrics. Track message rates by conversation. Alerts when any conversation exceeds thresholds that suggest it might impact the shard health. Proactive detection beats reactive firefighting. By the time users complain, we are already in trouble. Short-term mitigation includes rate limiting the hot conversation, slow down the message acceptance to prevent shard overload. Users experience slight delays, but the system remains stable. This buys time for long-term solutions. Communicate transparently if this is possible. Shard splitting moves a hot conversation to its own dedicated shard. This isolates its impact. The conversation still receives all its traffic, but other conversations of the original shared are no longer affected. This requires coordination between the application and database layers. Architectural solutions for known high traffic scenarios include pre provisioning dedicated resources. If you are launching a feature that will create a large active group, plan for it. Don't discover capacity limits during the launch. Now let's examine the storage tiering to manage the cost for the historical data. Now let's talk about storage tiering, which matches the storage cost to access patterns. Not all messages require the same storage characteristics. Recent messages need fast access. Users are actively chatting and scrolling through recent history. Old messages need only the occasional access. Someone might search for something from months ago, but this is pretty rare. Hot storage contains the recent messages, typically the last 30 days. This is high performance SSD backed storage optimized for read and write throughput. Most user interactions access only hot data. If 99% of messages read are from the last 30 days, optimize hot storage for this access pattern. Cold storage contains the older messages. This can be cheaper HDD, back storage, cloud archival tiers like S3 Glacier, or columnar formats optimized for compression. Access latency is higher, but the cost per GB is much lower. We are trading essentially latency for cost. Migration moves messages from hot to cold as they age. You should be running background jobs that identify messages past the age threshold and transfer them to the cold storage. This can run continuously without impacting the online traffic if properly throttled. You should be tracking the migration progress for operational visibility as well. Access patterns change when the users view old messages. They scroll back far enough to cross into cold storage. Latency increases noticeably as we fetch from slower storage. Consider preloading adjacent time ranges to make scrolling smoother. Some applications show loading indicators for old message sections. Cost savings are pretty substantial. If cold storage costs 10% of hot storage per GP and 90% of message volume is older than 30 days, tiering reduces storage costs pretty dramatically. You should be running the numbers for a specific retention policy and storage pricing depending on your use case. Now let's examine the caching strategies to reduce the database load. Now let's talk about caching, which reduces the database load and improves the latency through multiple layers. Client-side caching stores messages locally on users' devices. When opening a conversation, display the cached messages immediately while fetching updates from the server. This provides instant perceived performance. The user sees the recent messages in milliseconds while fresh data loads in the background. SQLite or similar embedded databases handle this pretty well on mobile applications. CDN caching applies primarily to media content, images, videos, and file cache at edge locations worldwide. Recipients can download media from nearby servers instead of the origin, and text messages don't benefit from CDN because they are personalized per conversation and small enough that latency don't matter much. Application level caching in Redis stores frequently accessed data, recent messages for active conversational metadata, user profiles, session state. This reduces the database queries for hot data. A well-tuned cache can handle the majority of reads, letting the database focus on writes. Cache forming proactively loads the expected data. When a user authenticates, we know that they will be likely opening recent conversations. Pre-fetch this data into the cache before they request it. When cache message, the data is already loading. This improves the perceived performance for common user flows. Cache-aside patterns has the application check cache first, fall back to the database on miss, then populate cache for the feature request. This is simpler than the write-through for chat workloads where the same data may be written by one service and read by another. Now let's examine the cache invalidation, which is pretty difficult. Let's talk about cache invalidation, which is one of the generally hard problems in distributed systems. The TTL-based expiration is the simplest approach. Cache data automatically expires after a time period. For messages, TTL can be longer since messages don't change after creation. Once written, a message content is pretty immutable. For user profiles, shorter TTL handles updates. Someone changing the avatar should see it reflected within minutes. Event-driven invalidation removes the cache entries when underlying data changes. When a user updates their profile, you should publish an event. All services holding cache copies of that profile receive the event and invalidate their copies. This provides faster consistency than TTL alone. Versioning tags cache data with a version identifier. Include the version in cache keys or as metadata. When data changes, increment the version. New reads request the new version. Old cache entries become orphaned and eventually evict through LRU. This avoids explicit invalidation across distributed services. Cache stampede occurs when popular data expires and many requests simultaneously hit the database. Without protection, we amplify the load at exactly the wrong moment. You should be using locking so that the only one request populates the cache while others wait for it. Or use a probabilistic early expiration to refresh the data before actual expiration, spreading the refresh load. Eventual consistency is acceptable for the most chat data. Seeing a slightly stale profile photo for a few seconds does not break the experience. Design details and invalidation based on how stale each data type can tolerate being. Messages need strong consistency. Profile photos can be eventually consistent. Now let's move to the group chat, which multiplies the complexity in several dimensions. Now let's talk about group chat architecture, which introduces the challenges beyond simple one-on-one messaging. Group metadata is stored separately from messages: name, avatar, description, creation timestamp, and settings. Updates to metadata don't affect the message storage. We can use a different database or data model optimized for the different access patterns. Metadata changes occasionally, messages arrive constantly. Member list tracks the current participants, store them as a set of user IDs with join timestamps and roles like admin, moderator, and member. The member list changes as users join and leave. Index for queries in both directions, group the containing for a specific user and users in a specific group. Message processing for group follows the same validation as one-on-one, but check group membership instead of direct friendship permission. The sender must be a group member. Some groups might allow external messages, but that's a pretty edge case. Fanout is a distinctive challenge of group chat. One sent message becomes end deliveries for end members. This multiplies the write loads if we are storing per recipient copies. It multiplies the delivery traffic as well. It can also multiply storage depending on our fanout strategy. A message to a 100 member group is fundamentally different from 100 one-on-one messages. Delivery targets all member connections, so look up sessions for all members. Push to all relevant gateways. Offline members receive push notifications. The chat server coordinates this fan out after persisting the message.